All right. Hi, everyone. Welcome to chapter 4. This chapter is on descriptive data mining. This is where we take just huge amounts of data from wherever we've collected it from and try to uh, get some information out of it. This is going to be talking about ways we can take information and see if there's a relationship between maybe the items that somebody buys at a supermarket and if we can better organize our supermarket, or it's going to be things like identifying potential demographics that we can market whatever it is we're selling our goods or services to. So let's get started. Um, why has there been this increase of data mining? Well, the amount of data that we have available to us just keeps getting, exponentially larger over time. It's just about doubling every year with all the various ways we're able to capture this information, whether it be through social media use or, web browsing or, just walking into a supermarket, the things you buy. So many different ways we're able to get this information. Also, we can warehouse the data even better. We're able to store a lot more of it, and the computers are now good enough that we can, analyze it. They're powerful enough now. The information can get from these data warehouses to our place of business in lightning fast speeds wherever we're at. And so it just has increased the ability for us to try to make usable information out of raw data. So we're going to talk about a few terms you're going to need to know. One is observation. So this is where you have a single entity and all of the recorded variables associated with that entity. So if I was to say, observation was on Monday, July 6th, and I recorded the temperature and the precipitation and cloud coverage or whatever. All of those things will be associated with this one observation. So the observation is the day, right? Or the observation could be a person, right? I've got one person and they gave us information, how tall they were, what they weighed, what their favorite color was, or whatever. You have a series of variables associated with one single entry in your list of your data table, right? But the observation is the set of all those variables with that single entity. Data mining approaches, this is talking about mostly machine learning, but supervised learning is where, let's say that we have given the parameters to the computer system. This is where we say, we've given what an apple looks like versus what a banana looks like to it. And so when it's sorting through images, it can look at the shape of the fruit and say, well, this is more likely to be a banana, and it'll count it as a banana, right? You give a specific parameters and guided instruction on how to sort things into categories. Unsupervised learning is more high level. This is where the computer system will describe those relationships between observations in some ways. It's trying to do the discovery for us. That's what the unsupervised learning is all about. So let's say we have all the data. We have to take some steps to turn it from raw data into usable information. So that's the data preparation part of our chapter. So data preparation, we're going to go through treatment of any missing data, identifying outliers, and then representing the variables. So when the data is in its original form, it's not been processed at all. Typically, that's called raw data. This uses the term dirty data. I've not used that or seen that in other textbooks, but raw data is more typically said, in my experience, at least from my studies and whatnot. We have to put them into some form for whatever it is we're doing to mine that data and turn it into information. So cleaning up the data, making sure that everything's in the same format. If it's a date, for example, making sure the date's in the right format. If it's a description of some kind, we're not going to have abbreviations on one entry that differ from abbreviations for what should be the same description on another entry. If there's missing data or whatever the else is, we use a lot of statistical methods to prepare this data. Sometimes there is missing data, and there are various descriptions of the missing data, and how you deal with that is going to differ. One option is if there's any observations that have any missing values in them, you just discard them. That's a clean way of doing it. Now, if you don't have a large enough data set, you might be missing out on something variable or valuable, rather, not variable. You could just toss out the entire every one of the variables. You can say, you know what, we haven't gathered enough information on temperature because half of the observations are missing temperature, so we're just going to take that out of our algorithm, out of our data mining that we're doing. We're just not going to use that. We just don't have enough solid information. Another option is to estimate it. Potentially, you could just take the average or median value and plug it into there in order to make it usable. That's going to vary based on what it is you're doing and how often you're doing it. That's going to be more of a decision process as to what feels right in that case. There are some sort of you can use regression or some sort of other algorithm to try to fill in missing values of some kind as well. So you do have some options, but we want to figure out why the data was missing. So there's 3 terms here. One, if it's a completely random occurrence, it's called missing completely at random, or MCAR. All right. If it's not completely random, meaning maybe one person is in charge of entering the data that day, or it's only missing if there's some correlation of some kind with another variable or something else, then it's missing at random. So you might look at the same, you might see those two things and think missing at random, missing completely at random sounds pretty similar, but completely at random, or MCAR, means that there's absolutely no correlation or reason for it. Now, it might be a random time when this one thing occurs. Maybe if it was so hot that day, if the temperature exceeded a certain amount, then we didn't gather something because it was too hot to go into out in the field and capture it, right? So we didn't get it that day because it happened to be whatever the case is. There's some correlation there, right? If this person's working, they don't do that part of it. They don't have the ability to do that, so we don't have it. So it's kind of random if they're on their shift. There's a random element to it, but not completely at random, because there's some kind of correlation as to why it's random, correlation with other variables in that observation. And then missing not at random. The reason the value is missing is related to the value of the variable. Okay, so not at random could be I've got to get a good example of that. I usually am better at examples. Let me grab an example for the from the book real quick, so I don't do that. Okay, so missing not at random. The probability of missing varies for reasons unknown to us. So it's not random, but maybe the scale has worn down that we're using to weigh something, and it's worn down to the point where it can't detect certain values. That's not random. There's something. There's some reason that it's happened there. Maybe we don't know exactly why, but it's not exactly random that's going on. Okay, so how do we identify if there are outliers or any kind of data that doesn't make sense? I'll give you an example from a study I was doing. We were looking at something to do with algae growth in the Tulsa water reservoirs. And there was an item where it was 91 degrees this day, 92 degrees this day, 91 degrees this day, 916 degrees or 912 degrees the next day, right? Probably wasn't 912 degrees outside. I think think we'd all be quite dead at that point. That's pretty hot for Fahrenheit. Pretty obvious that it was either 91 or 92. It was 912 was what it said. So pretty obvious what happened there, because it was 91 one day, 92 the next, 91 one day, and then 912, right? So probably the person was either meaning to type in 91 or 92 and just hit both keys at the same time on accident, right? So in that case, that was such an outlier. We felt pretty comfortable, the team that I was working on this project with, to just middle it, and we called it 91.5 that day, and we thought that was a fairly accurate and a reasonable way to deal with that data. But if you put data into scatter plots, as you've seen in chapters 2 and 3, when you made your scatter chart, you have maybe a trend going upwards, positive trend or negative trend, whatever. Well, you have a few those dots way outside of the trend line, right? So those are outliers. In my case, it was erroneous data. It wasn't an outlier. It wasn't abnormally hot that day. It was just incorrect, right? So really, observation is the best way to deal with it, but also to be conservative. Not to try to, like we did. We could have tried to average it out. That would have been one way to do average the weather, but we made a pretty reasonable assumption that it was 91 or 92, and middling it got us no further than half a degree off from one or the other. So there's ways to deal with outliers in erroneous data by just making it make sense, looking for it, and maybe exploring if you feel like it needs to be explored. Maybe there was just really busy that day, that's why the demand was there, or maybe there was something, some reason. Maybe a competitor was doing something, or was shut down, or had a sale, or something like that. Something changed your sales figures that day, so worth investigating, right? Just being aware of it and not just dismissing that. One of the reasons we put things into data visualizations is to make observations like that. So that's why chapter 3 is important, and why we're leading right into chapter 4 with this. So you visualize the data, you can see those kinds of patterns and trends. Sometimes there are just way too many variables being represented. We have too much information, and so we can run these through some sort of regression model in order to look at correlation between 2 or more variables. And sometimes those variables basically tell us the same thing, and we can improve the quality of our model by actually removing some variables, because they're kind of doubling up and making it harder for us to actually interpret it, because it's just too much information. We want to have things that are statistically significant in our models, and so having 3 variables that are basically telling us the same thing isn't helpful, right? So if it's rainy outside and the pool wasn't very busy, versus it was cloudy outside, well, it might be cloudy and rainy. Those 2 things could exist at the same time. So if they're both, when it's cloudy and when it's rainy, we're often slow at the swimming pool, then maybe those are kind of double dipping, whether or not they're telling us the same thing at that point. So if you have some variables are just not useful to what it is we're considering. So the example here, what it's talking about when it says that how you represent the measurements of variables, which variables to consider. Let's say that you're looking at, let's go back to groceries again, and you're looking at the amount of dollars spent by a household on groceries. May not really matter how much the dollar amount spent by groceries, right? So the average household spends $200 a week on groceries, right? Well, the amount of people in that household are going to differ, So maybe that only matters if you know how many people there are in that household. You can say the average household with 4 members, right? 2 parents and 2 kids, or whatever the case is. The average spent for that size household is this, right? Or if you say the average spent on groceries per week per person in the household is this, that starts to become more relevant. That's scalable and can tell us a little bit more information. So when you're looking at the measurement, so maybe amount spent a week or a month on groceries by household isn't as important when the household number varies, right? But we can maybe combine things as ratios, right? So by person in the house or something like that. All right, cluster analysis is going to be one of the things we do in our problem set. So let's talk about it briefly. We'll cover it more in depth with our problem set video. Often we want to know more about the people that we're observing in our data for marketing purposes, for example. So cluster analysis is can also be a part of, or at least it's close enough to that it's often synonymously used with market segmentation. So basically, if we want to identify certain variables that are similar between various individuals, we can know more about maybe their spending habits. So maybe this age group or this gender or this income range has this much more spend on these particular items, that maybe we know where we need to be pushing our marketing to, or how we market to those specific groups. Pardon me. And so with cluster analysis, you basically look at you said a certain amount of clusters. Maybe you want to have 4 or 5 different clusters, and look to see how similar the variables are in any one of those clusters, to try to maybe merge them into similar enough ones that we have the ability to market to those specific individuals in a more efficient way. K-means clustering specifically is something we're going to be looking at. K-means K is the number of clusters. And so what this means is we have each of our observations, our set gets assigned to one of those clusters, whether that be, and K clusters means one of 3 clusters, one of 4 clusters. K in this case is the number assigned to it. So cluster 1, cluster 2, cluster 3, cluster 4. K clusters would be that there's 4 clusters, so one of 4 clusters, right? Or 5 clusters, whatever it is that we've decided we want to split them into, or what makes sense. And so we can run our analysis and look at what it looks like after we group them into 3 clusters or 4 clusters or 5 clusters, and then kind of compare what makes sense when we look at all of our variables and measurements of our observations listed there. So we're going to work on a template that's going to kind of show us what it looks like if we did 3, 4, 5, 6 clusters, and then try to make a good decision on what makes sense for that. This formula we're going to mostly skip over. I just want to talk about this one idea, Euclidean distance. You're going to see that on your quiz. This is ways to measure dissimilarity between observations. We want our different clusters to be dissimilar from one another, right? If they're too similar to one another, then you'd want to merge them into one new cluster. So measuring specific dissimilarities lets us know if we have the right number of clusters, basically. So this is a specific formula. This looks very complicated. I'm sure some of you are panicking right now, saying, square root of squared numbers and all that. But you're pretty much going to be given these values. This is not nearly anywhere near as complicated as it looks like, and I'll explain this more in the quantitative video separately. But you take one number minus another number, square it, write that down, right? Take another number minus another number, square it, write that down. Okay, now add them together. you've got the number on your calculator, and then you just press your square root button. It's a pretty it's a shockingly fast formula that is not nearly as difficult to do as it seems might seem in the bottom of the slide there. So here's an example of to try to make what I just said make a little bit more sense. So you've got a financial advising company that provides personalized financial advice to its client. They want to segment its customers into similar groups so that the customers within one group are similar and dissimilar with respect to certain characteristics, right? So with each customer, they have a corresponding they've got measurements, 7 customer variables: age, female. What this is, so if you have binary variables, if you're only categorizing as female, male, you would have, you choose one, and you mark it 1 if it's correct, 0 if it's not. So 0 would be male for this customer, right? Income level, married, same thing, 1 if yes, 0 if no. Number of children, that would not be a binary. That could be just the number of it. Whether they have a car loan, whether they have a mortgage, right? So if they have a car loan, 1, if not 0. If they have a mortgage, 1, if not 0, right? So 61-year-old male, 61, 0 because they're not female. Income level, married, so 1, yes. 2 children, no car loan, no mortgage. That's what this is saying. And so we have all this information, and now we have a pair of customers, and we're looking to see how dissimilar they are. So based on all of those observations, there's a method of looking at that. Fortunately, you're not going to have to do much actual work on this. I'm going to give you one example on one question on the quiz with just 2 sets of variables, right? A very simplified version of that formula to do. And I'll walk you through how to do it by hand on that other video. So don't worry too much about it as you're watching this one. But we're going to run through you're going to have a macro. You're going to download a file that has a macro to actually do this for us. And you're just going to have to report on the observations you find. So don't sweat that formula too much, for right now at least. Euclidean distance is influenced by the scale. So just how far away something is, or when you have huge varieties in the number, the distances are going to get further, right? If you have salary, right, huge variation, versus 1 to 2 children, not as huge of a jump. So it is influenced by the scale. There's a way to convert these to z-scores so that you have a more relative distance. It kind of relativizes all of the various variables into a similar method to tell the distance apart from these observations and to help us do the clustering. Okay. We'll skip over this to the other video. We'll skip over this formula as well until the other video. I'll give you an example of that. Here's a chart showing us some how these values might be reported in some way to help us cluster them. So these are all binary variables: female, married, car loan, mortgage. Observation 1, you've got 1, 0, 0, 0. So you've got a distance measured between various ones. This chart's not something you're gonna have to work on yourself. Again, we're gonna have a macro that's going to run in Excel, and it's going to do all this for us. So we'll get into the interpreting of this more in the video. I just wanted to show you a similarity matrix is what this is called. Okay, so let's talk about ways things are linked. I'm going to just skip right to the next slide, and I'm going to skip back and forth between this slide and the next one as I show you an image that gives an example. So If you're looking at the similarity between two clusters defined by the pair of observations most similar, that's called single linkage. So this top left, let me get my highlighter on. So this top left one, observation 3. So 1, 2, and 3 are in one cluster. 4, 5, and 6 are in a different cluster. Single linkage is a specific term talking about the two closest ones. So 3 and 4 are closest to each other. 2 and 4 are a little bit further away. So 3 and 4, single linkage is between 3 and 4. Complete linkage looks at the similarity of pair of observations from each cluster that are most different. So 1 and 6 are furthest away. That's what this one does here. Group average, you take the distance between all of them and you average them out. So that's why you get this crazy pattern looking right here, right? So it's the average of 2 and 6, 2 and 4, 2 and 5, 3 and 6, 3 and 4, 3 and 5, 1 and 6, 1 and 4, 1 and 5. The average of all of those distances. So there's 9 recorded distances there. You average all of them out, and that's the group average linkage. And then the centroid linkage, you look at the median value of all of these similarities that are together. So you average out 1, 2, and 3, whatever that value is. You average out 4, 5, and 6, whatever that value is, and you measure it on the central value therein. So that's what those terms are referring to. How we're comparing. How we are comparing two clusters to one another, measuring the similarity. And there's different methods of doing that. Those are for those methods. Centroid linkage, we just talked about. Okay, Ward's method. So if you do merge two clusters, you want to make it so that the dissimilarity of observations is basically as little change as possible. All you need to know there is basically the definition. We're not going to do any actual work on this, but if you're asked about Ward's method, you'll need to know that this definition here. Same thing with these linkages. You're only going to need to know these for definition purposes, for quiz purposes. McQuitty's method, you're going to need to know how to do this, but it's actually pretty simple. You're going to need to know the definition for one. But let's say I merge A and B together, all right? The dissimilarity between A and B and then anything in cluster C is going to be the average of the old distances. So if we knew the distance between A and C and we knew the distance between A and B, average those two distances out, and now that's the dissimilarity between this new cluster, A, B, and C. So I'll go through an example of that on the other video. This is actually remarkably simple average. You just take this value, add them together and divide by 2. That's the answer. It seems complicated when it's worded this way, but we'll go through an example of that on the other video just to show you the math with the calculator and all that. Dendrogram, something you'll just need to know for definition purposes. It's a chart depicting a set of nested clusters during the aggregation process. That's what it looks like. You might be asked, what is this chart? And it's a dendrogram, and that's all you're going to need to know. We're not going to get too far into that. So here's the payoff for all of this. So K means clusters. You give a value of K, so maybe 3. Let's just say 3. All right. So the value is 3, just for the sake of this example. Then we're going to put all of the observations into 3 different partitions. This is cluster 1, cluster 2, cluster 3. Now, if I said the value of K is 4, it's going to make 4 different groups for us. It's going to look at all of the observations. It's going to assign it to one of those clusters. And then it's going to give a centroid value for all of those as well. And this is what that would look like. All right, so cluster 1 is all of the blue values. Okay, and we're looking at the age of the observations and the income of those observations. So we have a value, an average of all of these, so the mean of all the ages, the mean of all of the incomes, and that's this round circle here. And that's cluster 1 in blue. In red here, we've got cluster 2, and you've got the mean of all those. Cluster 3, you've got the mean of all those here. And that gives us pretty distinct goings on, right? We have one group where, so if we looked at cluster one and we were characterizing it, we would say that cluster one, this blue one, is, relatively young, and lower income. So cluster one here in blue is relatively young, lower income customers. Okay. And then we would say cluster two, this red one here, relatively older, higher income customers. And then cluster three, this green one, we would say relatively older, lower income customers. And that's all the information we have, and that's how we would describe them. So during the process of your problem set this week, you're going to be shown, a little map like this, and you're going to be shown, observations, like this. I might say cluster one, there are 12 observations, 8 observations, 10 observations. And then given something like this, we could say, okay, cluster one is relatively younger, low income. Cluster three is relatively older, low income. And cluster two is relatively older, higher income. And that's how you would describe those, because that's all, we're only looking at 2 variables here. If we wanted to know which ones of these were most distinct from one another, which were the least similar, we could say that cluster one and cluster two, by this score. So looking at this, we would see a score here of 1 and 2 as 2.784. That's the highest value on this chart. Cluster 1 and cluster 2, 2.784. We would say that clusters 1 and 2 are the most distinct from one another. Then we look at the smallest value, and that's 1 and 3. So 1 and 3 are the least distinct from each other, right? Why might that be? Well, the younger you are, the lower your income. The older you are, the higher your income. You're following a pattern here. As you get older, you get more income. But cluster 3 here is very dissimilar from this in that they got older, but they didn't get more income. So there's something different about them than there is about the people on this. This is, it could be considered an actual timeline, right? But something changed with this group of individuals. Maybe they didn't get a college education, or maybe they live in a rural town, or maybe they work for nonprofits and they are lower income individuals. Maybe their partner makes more, and so they're able to, afford to be able to do more charitable things, or whatever the case is, or they, whatever it is. As they got older, their income did not go up. So there's something different about the individuals in this group, right? And so they are more dissimilar from the others, even between 2 and 3, 1.9 versus 1.5, right? Where 2 and 3 meet. They're a little more similar because they're both in the same age range. Right? So that tells us what's different, what's distinct about the individuals in various clusters after that. So whether we use hierarchical clustering or k-means clustering, let's say we have a small data set, we would maybe use hierarchical. If you just want to observe how those clusters are grouped together, you could use hierarchical. Doesn't sound right when I'm saying it. If you have how many clusters you want to use, and have a very large data set, you would use k-means clustering. If I want 4 distinct groups, or 5 distinct groups, or 3 distinct groups, you could run this. If the observations are able to be averaged out in some way, then k-means clustering would be appropriate. You can average the age, you can average the income. There's some things, some categorical values that it's not appropriate to average. It wouldn't make sense as an average. So you wouldn't use k-means clustering. You would use the hierarchical clustering values. All right, last thing we're going to talk about are association rules. So this is our, we associate if-then type of situations. So association rules are if-then statements, which give a likelihood of items being purchased together. So we're making it very clear by looking at items in a shopping cart, right? Things you bought in one transaction at a grocery store is going to be the example on this slide, and also the example on your problem set. So antecedent, this is the items corresponding to the if portion, meaning if I buy this, okay, if I buy this item, then consequent, right? That should be, well, okay, let's look at the root. If you're trying to remember what's what, ante meaning before, right? Consequent, pretty similar to the word consequence, right? Of your actions. So the item set corresponding to the then portion. So if you buy this, then probably you are going to buy this item also. Just thinking right now, without me going to the next slide, what's something you can think of, right? Pause the video, okay? What's something you can think of at a grocery store where if I buy this, I might buy this also, okay? I'm gonna pretend like I'm pausing. You pause it. Just think about that for a second, all right? Okay, we're back. You've unpaused. Thank you. So maybe if you buy chips, you buy dip. Maybe if you buy shrimp, you buy cocktail sauce, right? Maybe if you buy peanut butter, you buy jelly. Maybe if you buy meat or cheese, you buy bread. These are things that are possibly likely that if you buy one of the things, you then buy the other thing, right? And so what does that tell us? Well, if you're laying out the grocery store, and this doesn't have to be a grocery store, this could be a retail store of some kind, right? If you buy this phone case, you might also buy this screen protector or something like that, right? If you're organizing a retail store or whatever it is, it helps you to lay out your store in a way to present the items to maximize sales. So this helps us with organizing of that, right? Support count of an item. So this is going to be the number of times the transactions included that item set. Let's look at this real quick. So transaction 1 had all these items in it, right? Bread, peanut butter, milk, fruit, jelly. Transaction 2, bread. We see jelly again. We see fruit again. We see peanut butter again. All right. This one, whipped cream, fruit, chocolate sauce, beer. Very dissimilar from these other ones. All right. So we haven't noticed anything specific here, but we see jelly, bread, and fruit again. So if we're seeing specific things, we can look at bread and then look at all the times bread showed up in the same transaction. We can look at peanut butter as the antecedent and then look at all the times these other ones, if there's support for those other items as a consequence of that. I'm just going to explain what these mean, but I'm not going to go through the formulas on this one. I'll do this on the other video. Confidence level, so basically how reliable we can rely on these association rules. Look based on the support of these things. Lift ratio helps us identify the usefulness of that rule, so how often that rule is good at identifying it. Greater than 1 would say that there is some usefulness to the rule. Less than 1, probably not. That's a general value, but typically you're looking for something greater than 1 in this case. But again, we'll go through that a little bit more in depth on the other video. Evaluating it, you're ultimately evaluating it based on if it's actionable, if it explains the relationship well, and if we can do something about it. So here's Walmart. They've looked at all these things. If a customer purchases a Barbie doll, then a customer also purchases a candy bar. Okay, well, maybe we put some Barbie accessories in the candy aisle. Maybe we put the toys next to the candies, right? Or something like that. Maybe we in the checkout lane there's specific items, or maybe we tell our providers we need a Barbie themed candy bar or something to create this product. So if it's useful, it's well supported. If we can find strong evidence of it, then perhaps we can do something about it. So here's what that might look like. Here's an example. This is going to look very similar to the work you're going to do this week. But basically, we're going to calculate a confidence level. We're going to look at items, whether it be one item or 2 items specifically as the antecedent, and then to see, if I buy bread, do I buy jelly? If I buy bread and fruit, do I buy jelly? If I buy fruit and potato chips, do I buy soda? And then we're going to see the number of times those come up in the in the item chart. We're going to look at the lift ratio and calculate the confidence level and all that. But again, we'll save that for the problem set video. All right, guys, make sure you read along with the chapter, and I'll have the full PowerPoint available for you to review as well. And we'll see you in the corresponding problem set video. Thanks, everyone.